Hi friends, today I'm going to make sure you find all of your trig derivatives, and I'm going to show you some notation that I think has been thrown at you and maybe not really talked through very thoroughly, so I'm going to try to be kind of thorough about it. First though, this is a graph of sine, and I want to go find the derivative of sine. I'm not going to prove this one to you. I'm not going to go through a proof, but we are going to just kind of analyze the graph here. So if you remember from last week, if you have a function and you're asked to graph its derivative, the first thing you should try to do is find all the horizontals. So it looks like it go horizontal here, and here, and here, and then this one. So these should be zeros on the graph of our derivative. And then you analyze in between. So between these two zeros, this piece has a negative slope, but it's not like super negative. That's not very steep right here. So I think I'll dip it down, but then make sure you come back up to hit the zero that you know you have to go through. And then the same kind of pattern throughout. So this piece has positive slope, but it's not super steep. So we'll go up and make a positive slope, come back down, rinse and repeat. There's your negative slope, come back up, positive slope. I bet it heads back down. This is a graph, kind of cosine. The derivative of sine is cosine. So again, that's not a proof. That's just kind of a visual of why that's true without going through the specifics, because I don't want to bore you with a proof. I'm curious what you might think if I give you cosine then and ask you for its derivative, what you might think. You might want to say sine and you'd be really close, but it's actually negative sine. And if you take a second to plot those, you'll see why. Okay, using those two, so derivative of sine is cosine, derivative of cosine is negative sine. We are going to go prove the derivative of tangent. So I should be numbering these. So this is derivative 1, this is 2. Let's go to tangent. Tangent we're going to think of as sine over cosine. And we're going to go find its derivative using quotient rule, which you learned on Tuesday. So I haven't thrown any new notation at you yet. I'm still just using our primes. But notice up here I used y prime. Here I'm using f prime. I'm going to try to use everything interchangeably. Here we go. Quotient rule says low, cosine, d high, derivative of the high. So derivative of sine I just learned is cosine. Low d high minus high, you just write it. d low, derivative of cosine is negative sine. So low d high minus high d low is negative sine. I'm going to go ahead and make this a positive times a sine. Low d high minus high d low all over low low. So cosine squared. And I'm going to write it that way for right now. Okay, well if I clean, this is cosine squared plus sine squared over cosine squared. And yes, it is. Sure it is, but nobody's ever going to write it that way because cosine squared plus sine squared is 1 over cosine squared. And yes, it is. Sure it is. But again, nobody's going to write it that way. They're going to write secant squared. The derivative of tangent is secant. So, I mean, you know some calculus now, and we've been talking about slopes of line segments. And we did average rate of change was the slope of the secant line versus instantaneous rate of change is the slope of the tangent line. Tangent and secant belong together. Like those vocab terms, they go together. So the derivative of tangent being secant squared is kind of poetic. They belong together. Tangents and secants belong together in math. All right, so for 4, I'm going to do notation with you. No, I'm not. I'm going to write it, but we'll talk about what it means in a second. That is derivative with respect to x, d dx of cotangent. So I don't know if you're catching on to any patterns here, but if tangent and secant go together, then cotangent and cosecant must go together. But the issue here is it's going to be negative. Oh, that's not how you do cosecant. Cosecant squared. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. And you prove that one the same way. You could do a cosine over sine and then do a quotient rule on it. All right, let's do secant. Let's go take the derivative with respect to x of secant. We're going to do this one with quotient rule too, because we're going to take the derivative with respect to x of 1 over cosine, and we're going to do a quotient rule. So quotient rule says low d high, derivative of the high. Well, the high is 1. The derivative of a constant is 0. So low d high minus high is just 1. I guess I can write it. I don't want to. I guess I will. D low, derivative of cosine is negative sign, so it's again a positive, a plus. All over cosine squared, all over low. So lots of quick cleaning here. The 0 goes. This is just sine over cosine squared. And again, yes, it is. Nobody's ever going to write it that way. Here's what they're going to write. They're going to have 1 over cosine times sine over cosine so that they can call it secant tangent. Oh, look, they're back together again, just like we always wanted. The derivative of secant is secant x tangent x. Okay, so last trig function would be cosecant. I'll count to 5. Can you guess? That's right. You're so smart. It says negative cosecant cotangent. So cosecant and cotangent belong together. Notice that there's a pretty clear pattern with these. How they're all almost the same, but then half of them are negative. I mean, that's good news, bad news for memorizing because it means you're going to miss negatives here and there. But you do need to have these memorized. You have to be able to recite these very, very quickly without any prompting or looking things up. So as you're practicing in your practice assignment that's coming, have your notes out and whatnot, but see how much you can do without them. All right, the other ones that we need to talk about because they never really happened and they need to, so these are extra derivatives for you today, are e to the x and its inverse. The derivative of e to the x is e to the x. That's going to be the easiest one that I ever have you memorize. It's not very intuitive as to why that's true. I will prove it to you in class in a couple weeks. We're just not ready for it yet, but it's a good one to know quickly so that we can use it in problems. But if we're going to know that one, we should know its inverse. The derivative of natural log of x is 1 over. So those aren't terrible. I mean, I'm saying that. I already have them memorized. I shouldn't say anything. Maybe that's all terrible. I'm sorry that it's all terrible. Add those to your memorization list. I think you're up to 14 rules, if I count product rule and quotient rule as separate rules. All right, well, here's why I want to throw those in, so that I can give you questions to take derivatives of, like, let's go differentiate this function x squared plus sine over e to the x. And we're going to do that one with a quotient. I don't know why I'm doing a bunch of quotient rule today. Quotient rule says low, just write it. D high, derivative of the high. This first one's a power rule. Derivative of sine is cosine. Low d high. Minus high, you just write it. D low, derivative of e to the x. Easiest one you'll ever have to know is e to the x. And then all over, I'm going to write e to the 2x. E to the x squared is e to the 2x. That's great. That's fun. One more. What if I give you a function like, I don't want to do another quotient rule, but you don't know anything. We'll do x squared times secant. X squared is boring. We're going to do square root of x times secant. Okay. Well, it's still not terrible, but it is a product. You have to do a product rule here. Before I start, I want to rewrite this so that I know it's x to the 1/2, so I can see my power when I'm doing my power rule. Until you get really, really quick at those, you should always try to rewrite them. And we're going to go write the derivative using product rule. Product rule is first, you just write it, derivative of the second. So first was that, second is here, derivative of secant is secant x tangent x. Don't lose this x. It's not secant of tangent x, it's secant x times tangent x. So first derivative of the second plus second, you just write. Derivative of the first is going to take a power rule. So I'm going to pull the power and subtract 1. And I have zero interest in cleaning anything up, although I know I could. And if I were doing book work and I check the back of the book and they don't look the same, it might be because they cleaned up and I did not. And that's okay too. Okay, last thing is this notation, this ddx business. ddx means take the derivative. It's an operation like this is an operation or this is an operation. It doesn't mean anything without something inside it. So I might put a 16 in here. I might put a function in here and tell you where x is going. I have to put something in this derivative. So sometimes we put our something, like if I'm having you differentiate y, we could put it here, or we could put it next to it, which is how I was writing some of those problems above, ddx, and then just off to the side. You can think of it like a function. But like a fraction, where you can just write it separate. Let's talk about this version, this dy dx. I love this notation because it all flows together really well. D doesn't stand for derivative. D stands for delta. And so, I don't know, it's been a while since you were in Algebra 1, but delta used to be these triangles to you. That's not a triangle. Oh my goodness. Delta y over delta x. Oh, look, it's a slope again. That's slope, change in y over change in x. The reason we go from a triangle to a D is triangle, it still means delta, but this is your algebra version of a delta. So that's your algebra slope. Your change in y, change in x is over a large distance or any distance. It's your secant slope. This is your calculus delta. And it's for instantaneous rate of change. So that's that notation. If anybody ever asks you to do this and gives you something in here, they could ask it that way, or they could put it up here. That's less common. They usually write it off to the side, but it's the same thing. They're asking you to take the derivative, find the rate of change with respect to x of this function. It's a little bit nicer because I could just put equals and then my awesome derivative answer, as opposed to having to write two separate lines where I say, hey, f of x equals this. Now separately, please go find f prime of x. And they're like separate thoughts. So just, notation, because notation is fun and important. All right, friends, I think that's the end of this unit as far as new things to learn. We're just going to practice taking lots and lots of derivatives for a day or so, and then we got a test coming at us next week. So get on it. Keep practicing. See you soon.